All right, so in section 1.7, we talk about this idea of linear independence. Now, we've already kind of dealt with it in some sense, but as with many things in linear algebra, we like to kind of revisit it and strap on a little bit more rigorous terminology, which makes it a little better in the moving forward. So let's talk about first of all what it means to be linearly independent. Linear independence or linear dependence is a property of a set of vectors. So we say, we'll look at a set of vectors, say three vectors, and we'll say, are these vectors linearly independent? Or a set of seven vectors, are they linearly independent? Or even a set of one vector, and that's going to be trivially linearly independent. But it's a property of a set of vectors. So basically, here's the rule. Here's the definition. A set of vectors. So here's our set, v1, v2, however many we have. Let's not use vn, let's end it at vp. So there's our set of vectors, could be any number of vectors. In Rn is linearly independent. The set is linearly independent if the vector equation, oh, we were doing so great there. If the vector equation x sub 1 times the first vector, so x sub 2 times the second vector, so some constants. So we've just basically got this linear combination of our vectors. If that linear combination, when set equal to 0, has only the trivial solution. Okay, so that's the definition. In order for a set of vectors to be linearly independent, then you look at this this equation, and it's always set equal to 0, and it should only have the trivial solution. Now, obviously, 0, 0, 0, all of the x sub n's set equal to 0 is a solution. But if that's the only solution, then that set is linearly independent. Alternatively, we could say it this way, or this is kind of what being linearly independent means. It basically means one vector, one of the vectors, or more, is not a linear combination of the others. Now, this is not 100% accurate, but it's okay for us to think of it this way. We can say the vectors are independent if you can't write one vector as a linear combination of the others. So these two things go hand in hand. All right, so that's what it means to be linearly independent. Now, we've looked at this before. We've looked for solutions to this equation before. So let's just do a quick problem that illustrates these points here. So here we go. The question is this. Are the vectors v sub 1 equals 1, 2, 3. V sub 2 equals 4, 5, 6. And V sub 3 equals 2, 1, 0. Independent. Or if they're not, then they're dependent. So that's the question. Are those vectors independent? So what we're trying to do is we want to consider the equation some constant times v1 we want to solve the equation is the more precise. X sub 2 times 4, 5, 6 and x sub 3 times 2, 1, 0 equals 0, right? So this would technically be written as a bold 0, but remember, when we kind of write that as use that to represent the 0 vector. Okay, so that's the question. We want to look at that. We want to solve that equation. And if the only solution is the trivial solution, then they are independent. You cannot write one as a linear combination of the other. You cannot build one out of the other two. So that's what we're trying to do. And we looked at this last section, right? We said, hey, how do we solve this equation last section? And we learned, or we saw that this equation, well, we'll put all the steps in here. I think it's important, right? So this equation looks like this. This will really look long and drawn out, but it's important you see where everything comes from, right? So when I multiply the x1 into that first vector, it becomes this, right? Then when I multiply the x sub 2 into the second vector, it becomes this. And x sub 3, and we want to know, when does that equal 0, 0, 0? And of course that leads to this, x sub 1 plus 4x sub 2 plus 2x sub 3 equaling 0. And like I say, this is not something that is surprising to you, and you may be wondering why we don't just jump right to the end. But you need to see where the end comes from and how we get there. Guess we don't need that there. We'll just leave that like that, equals 0, right? And so we could then ignore the, right? I mean, if you've got one vector equals one vector, then that must mean the entries equal each other. And in the end, that leads probably where you wanted to go right at the beginning, to this augmented matrix. And I'm going to, well, we'll talk about that here in a second. 2, 5, 1, 0, 3, 6, 0, 0. And I'm just going to do this because I think we want to get used to this, right? The book just refers this, tells us this is augmented, and we're supposed to remember that there's that dotted line right there, right? Or that these are three equations equal to 0. So, but we're going to do it like that. Okay, so we know if we want to solve that system that we throw it into this augmented matrix, and that we need to look at its row-reduced echelon form. And we find that the row-reduced echelon form of this thing looks like this: 1, 0, negative 2, 0, 0, 1, 1, 0, 0, 0, 0, 0. And we notice, hey, we've got a free variable right here. And that tells us there are an infinite number of solutions. And that means, 0, 0, 0, 0 was already a solution, or 0, 0, 0 was already a solution, but they're an infinite number, so these vectors, because the trivial solution is not the only solution, these vectors are not, well, we'll write it down here, because the trivial solution is not the only one. The vectors are linearly dependent, which means we can write one of them out of the other two using a linear combination of the other two. Now, actually, in this case, you can write any one of them out of the other two. But, the first part of the question is they are dependent. And so we've got that. Now, if we wanted to just take the information that we have a little further and understand it, based on this row reduced echelon form, we know x1, x2, x3 is free, so let's call that t. x2 is 2t, and x1 is negative t. So if I say let x equal, of course, let t equal 1, then the solution x1, x2, x3 is 2, negative 1, 1. So that means the equation that we had is 2 v1 minus v2 plus v3 equals 0, right? Using our x, I think the book refers to them as weights or something like that, but there's the combination, and there are any number one of those combinations depending on what we let t equal. But notice if I say move the v2 over to the other side, 2v1 plus v3 equals v2. Look at that. I've just written v2 in terms of the other two. In other words, I could build v2 using v1 and v3. I don't need v2. Alternatively, again going back to the original, I could do the same with v3, right? v3 is a v2 minus 2v1 as I move, as I just algebraically solve for v3. So I could write v3 using the other two, and I could do same for v1. I think v1 will equal what? 1/2 v2 minus 1/2 v3. So notice how I can build any one of by virtue of the fact that this equation has a non-trivial solution, I can build any one of the vectors out of a linear combination of the others. Therefore, they are not independent, they are dependent.